Okay, this video is going to get a little tedious, but I'm going to try to avoid as much tedium as possible in like the homework and stuff. I'm not going to ask too many questions with problems like this. So remember the fundamental theorem of calculus, I've said it many, many times, is that the antiderivative or the definite integral of a rate of change is the total change. Rate of change oftentimes can be thought of as a derivative. Okay. And so we're going to be evaluating these now. We finally have antiderivatives. So all we're going to do is use the antiderivative and plug in the end number and the start number and take the difference. That'll give us that total change. So when we're doing this, we have this abbreviation for this right-hand side. And the abbreviation is we write a vertical bar to the right of the function with a and b. This won't make too much sense why we do this just yet, but hopefully it'll make sense when we do this example. So let's start by doing this the new way, the 3.3 way. We've already talked about how to do this earlier using graphs. Remember, this is the line y equals x, and we're looking at the area under the curve from 1 to 3. That area is a trapezoid, a rectangle and a triangle. We've already talked about how to find this area. So we'll do it both ways. We can do this the old way. 3.1 uses this picture, but let's use the fundamental theorem of calculus. Fundamental theorem of calculus says that this integral is the total change of the antiderivative. Well, what is the antiderivative? Because if we can find the antiderivative, then we just evaluate it at the start and at the end and take the difference. So having this middle step just cleans things up a little bit. What's the antiderivative of x? We'll need the power rule. Think of it as like x to the first power. So we add an exponent and divide by that exponent. Why don't we, hold on. Why don't I have a plus c in this formula? The antiderivative has a plus c. Well, basically because what we have is we basically have f of b plus c minus f of a plus c. So no matter what constant it is, the constants ends up canceling. So we actually can totally ignore the constants here, which is nice. We only need the plus c for indefinite integrals. For definite integrals, we don't need the plus c. So our antiderivative is essentially x squared over 2. Plus any constant, but no matter what constant you choose, you'll get the same answer. So we just choose our constant to be 0. And now we use this notation. This says plug in b and then plug in a and subtract them. Also, we know what a and b are here. A was 1, b was 3. So we plug in 3 and we get 3 squared divided by 2. Then we plug in 1. We get 1 squared divided by 2. And now we simplify and subtract. Fundamental theorem says the integral of the rate of change is the total change of each thing. So this is f of b, the antiderivative at b. This is f of a, the antiderivative at a. This is 9 halves minus 1 half. That's 8 halves, which is 4. Well, look at this picture up here. Is the area 4? Well, this is the line y equals x. So that tells us that if that's a width of 1, this is a height of 1. If this is at, oops, this should be a 3 down here. This should be a height of 3. So this rectangle, right, is 2 by 1. And this triangle is 2 by 2. So in 3.1, we'd say the area is the rectangle, which is an area of 2, plus the area of the triangle, which is 1/2 base times height. which is also 2. And of course, you can say, Jason, the old way was way easier. Yeah, it was. But the new way doesn't require us to graph, and the new way works for so many functions. We could really only do lines in 3.1. But now we can do so much more, and we will. So let's do another problem. Find the area between the graph of 3x squared, which is a parabola, the horizontal axis, and when x is between 0 and 1. Let's make a little graph of ourselves. This is basically the graph of x squared, but it's been multiplied by 3, so it's a little stretched. I'm not very good at graphing. That's okay. We want the area under this curve between x equals 1 and x equals 2. So we're looking for this area right here, under the graph, above the x-axis, between these. And we know the area under the curve is a definite integral. Specifically, the definite integral, x is going from 1 to 2. Our function is 3x squared, and we're integrating with respect to x. So we find our antiderivative and evaluate it between 1 and 2. What's the antiderivative? Well, let's use the power rule. Add an exponent, divide by that new exponent. Simplifies, our antiderivative is just x cubed, evaluated from 1 to 2. So we plug in 2. We plug in 1. Oops, that's not how that works. We plug in 1. And we subtract them. We'll get 8 minus 1, which is 7. Another good way to check these is to remember that we can evaluate these with Desmos. The integral from 1 to 3 of 3x squared dx. It's great that we can check our answers. We're integrating from 1 to 2. And it's 7, just like we expected. Okay? And there we go. That's the answer. One other thing I want to warn you about for these types of problems, let's say you're looking at the integral from 0 to 2 of x squared minus 5. You'd use the power rule to get x cubed over 3 minus 5x, and we'd want to evaluate that from 0 to 2. When you plug in 2, you're going to get 2 cubed over 3 minus 5 times 2. When you plug in 0, you're going to get 0 cubed minus 3 minus 5 times 0. These parentheses are important. When you're using the fundamental theorem of calculus, make sure that you're subtracting the whole thing. You're going to have to distribute that negative or simplify on the inside. Not the best example because this turns out to be 0. But the idea is if you have multiple terms in your antiderivative and you're evaluating, make sure that you're evaluating within parentheses. Watch out for that. Otherwise, you may get the wrong answer. Let me know if you have any questions, and we'll get, what are we doing in the next video? Next video, we're getting into some applications, and then we'll have some more homework practice after that. Bye-bye.